Okay, hello everyone. Let's go ahead and take a look at using vector methods to calculate volume and area. Now we'll start off with area, and remember from our past experiences with working with area, if we wanted to calculate the area of a triangle, we could just say 1/2 AB sine C. Now let's go ahead and assume that in this case we have two vectors instead and put those into standard position, and if we go ahead and join the two arrowheads with a dotted line, let's go ahead and use that green dotted line, then we come up with an area of a particular triangle that is created by those two vectors. So now we said that, well, it's being that it's still a triangle, and we know that this angle here is the angle that is created by the two vectors when placed in standard position. We can go ahead and use the same concept here and say that this is going to be 1/2 times it by the modulus of the A vector, times it by the modulus of the B vector, times it by the sine of theta, because that's the angle that is created. And what we know from before is that, well, that's the same thing as the A vector crossed with the B vector. And then what we need to do is we just need to make sure that we're taking the modulus of that. Because remember, the cross product or the vector product is going to give us a vector, and in order for us to go ahead and calculate what that area is, we need to go ahead and find the modulus of that normal vector. So notice the nice thing about this is it no longer necessitates us finding theta. We can go ahead and find directly using vector methods what the area of a triangle is. Okay, now let's go ahead and move on then, and let's consider the parallelogram. Now notice that if we go ahead and again start off with two vectors, A vector and B vector, put them into standard position, we've got a particular angle theta, we know that the parallelogram is actually just going to be the same thing as 2 times the area of the triangle. And therefore, since we know what the area of the triangle is, we can just go ahead and say that the area of the parallelogram is just going to be the cross product of AB and then find the modulus of that. Now, with regards to the parallelepiped, what we have here is something that's called the scalar triple product. Okay, and what we have here is the A vector dot with the normal vector that is created by B cross C. And so what we have here is just take a look at how we can go ahead and create this parallelepiped. And notice that one thing, it looks like this is actually going to be a right angled prism with a rectangular base. But the thing is that we don't have to have it rectangular anymore. It can be any 3 vectors that you have that are in standard position that then go ahead and create this 3-dimensional figure, which is called the parallelepiped. Now, if we wanted to go ahead and do this, all we needed to do is go ahead and take the scalar triple product and actually take the absolute value of that. So we have A dot with the normal vector created by B and C. And so using the determinant method, we can go ahead and find out what that particular value is. And then we need to go ahead and make sure that we keep it positive, and that's why we use the absolute value signs. Okay, now with regard to this, we'll go ahead and take a look a little bit more in class as to why that is actually true and how that comes out to be that way. Okay, so just to go ahead and wrap up then, using vector methods, you can calculate the area of a triangle, the area of a parallelogram, and then you can extend it to the 3-dimensional case of the parallelepiped. Okay, so we'll take a look at some of those problems in class, and we'll see how we do. Okay? Bye-bye.